Section 2.2 is on the definition of a limit. The objective here is, given a function, determine the limit of the function and use the definition to prove it. So let's start out with a simple definition here of what a limit is, and I guess the simplest definition I can give you is it's a y value. But to expand on that a little bit further, I'll say that it's a y value that a function approaches as x approaches a given value. So in other words, as x gets closer and closer and closer to some number, the question is, what's the corresponding y value that your function is getting closer and closer to? So it's a y value you're finding when you're finding a limit. There is a notation that we use here to describe a limit, and here it is. We say that L is equal to the limit as x approaches c of f of x. Notice that the notation there, we use the abbreviation LIM there for limit. You'll also notice in the notation there that we don't say x is equal to c, but we use this arrow here to indicate that x is approaching c. So the definition doesn't have anything to do with what's happening right at c, but rather what's happening as I get closer and closer to that value. And again, it's read as L is the limit as x approaches c of f of x. Sometimes we switch that around a little bit, and we might say L is the limit of f of x as x approaches c. But those, of course, mean the same thing. Let's take a look at an example here of a function that we can represent what that limit notation there is saying. I'll just sketch some function. It really doesn't matter what a function looks like here. We'll call this f of x. And let's say that we're considering some point here. We'll say that this is our value of c right here. And so as we get closer and closer to that value of c, on both sides of our function, that is, or on both sides of x equals c, as I approach from the left side and as I approach from the right side, the question is, what's the corresponding y value that my function is approaching? And in this case, they're both approaching this value about right here. That's the value L that we're talking about. So as x approaches c, L is the y value that we're approaching. All right, so let's take a look at a example here. Example 1 there on page 34 in your book. It says, state whether the function graph has a limit at the given x value and explain why or why not. If there is a limit, give its value. Okay? So let's use that formal notation there that we just learned in order to write these out. So let's start out at x equals 1 there. So we'd say that the limit as x approaches 1 of f of x is equal to some value here. And again, what you have to consider when you look at the graph of this, as I approach this value of 1 from both the left side and the right side, I've got to look at the graph and see, as I approach from the left, what value am I approaching, and as I approach from the right, what value is my function approaching, what y value is it. And based on the sketch there, even though I can see that there is a hole in the graph there, I can still see that from the left and the right side, I'm approaching that value of 2. So as x goes to 1, my y value that I'm approaching is right here at 2. That is our limit in this case. So the limit is 2. Let's take a look at the next point there. So let's take a look at x equals 2. So the limit as x approaches 2 of f of x. Again, do the same thing. So here's our value of 2. And we've got to consider what's happening as I come into 2 from the left side and from the right side. Well, you trace your function there from the left side and the right side. I can see that from the left side, it's approaching a value of 5, as well as from the right side. So in other words, as we come into x equals 2 there, we're approaching the same value of x equals 5 from both the left and the right-hand side. So that is our limit. And finally, they asked us what's happening as we approach 3. So the limit is x approaches 3 of f of x. And again, do the same thing. From the left side, I can see that as I approach this value of 3 from the left side, it looks like I'm approaching a value of 10. On the right-hand side, I can see that my function is approaching a value of what looks like 8. So because of the fact that I'm approaching one value from one side and a different value from the other side, that means that in this case, the limit does not exist. We can use DNE to represent does not exist for us. Okay, so there's a graphical representation of a function and how we can find the limit of that function at different points in this case using just the graph. All right, on that graph that we just looked at, there are some discontinuities that showed up there. There was a hole in the graph, and then there was also a kind of a step there that you saw at that last point we considered. And those have some special names, so I'm just going to put those up here for you. The first point at x equals 1, it's not actually a point, the first discontinuity we saw at x equals 1 was what we call a removable discontinuity. It's a removable discontinuity. Both these are discontinuities. This first one is called a removable discontinuity because of the fact that we have just a single point that's been removed from this function. And if we substitute that point back in, we would no longer have a discontinuity. So it's called a removable discontinuity. The second one that we saw at x equals 3 was what we call a step discontinuity. Some books will refer to this as a jump discontinuity. They mean the same thing, but it's a step discontinuity in our book is what our author will use. And the reason they call it a step discontinuity is you can see as I move from left to right that I have to step down at that point, in this case, to continue on this function. Sometimes you step down like we have here, and other times you step up. And if that happens, we call that a step discontinuity. On this one, by the way, you can see that at x equals 3, they filled in the circle there at the top there. This function is defined at x equals 3. It has a value of 10. And you'll notice that at the other point, that it's got a hole in it. Of course, in order for it to be a function, you can only have one of those points filled in. Otherwise, if it was filled in both places, you would no longer have a function because it would not pass the vertical line test there. But you could have one of those filled in and the other one not filled in like we have here, or they could both be open. They both could be not filled in, and we still would have a step discontinuity there. All right. That leads us to the formal definition, and you'll see the formal definition on page 34 in your book, and I want to go through that formal definition with you so you understand what the definition first of all says and what it means. And there will be times when we need to go back to this formal definition, especially on some functions. It has some tricky points in those functions where it has some sort of discontinuities or other things might be going on. And it's really the definition that's going to help us understand what the limit is. Okay? And so, like I said, this definition is a little bit trickier. You're definitely going to want to review it a couple times and go over it again and again just so you can get the idea of what it's trying to say here, but I want to run through it here with you. Here's the formal definition. It says, L is the limit as x approaches c of f of x, if and only if the following happens. For any epsilon greater than 0, that's the Greek letter epsilon, the lowercase Greek letter epsilon, which is going to be a small number. For any epsilon greater than 0, there exists a delta greater than 0. That's the Greek letter delta, but that's the lowercase Greek letter delta. You'll recall the uppercase Greek letter delta is the triangle. It looks like a little triangle. For any epsilon greater than 0, there exists a delta greater than 0, such that if x is within delta units of c, so delta is going to be used as some sort of restriction that we put around this value of c that we're approaching. If x is within delta units of c, but not equal to c, x does not have to equal c, then f of x is within epsilon units of L. So the epsilon is going to be used as some sort of a restriction that we put around our limit L. Delta is a restriction around C, and epsilon is a corresponding restriction around L. All right, let me draw a sketch of this to help illustrate exactly what this definition says, but certainly that's a definition that you're going to want to go over several times, perhaps in your mind there and in your head there, and look at this picture to kind of help tie all that definition together. But let me just sketch a function here. It really doesn't matter what our function looks like. I'll sketch a function that looks like this. We'll call this f of x. And let's say that we're talking about approaching some value. We'll call this c right here. And let's say that that is the point on our function at c. And based on what we just talked about with what a limit is, that would be the value of L, the limit of this function. So, the definition there says, let me just scroll back up here so we can see this. The definition talks about some value epsilon for any epsilon greater than 0. And we know that epsilon is somehow related to this restriction that we're putting around L. For any epsilon greater than 0, and I know that epsilon is a restriction around L. So let's draw that in there and what that's actually representing. Basically what I'm going to do is draw a horizontal line here that is epsilon units above my limit, and I'm going to draw another horizontal line that's epsilon units below that line there. So in other words, this distance right here is epsilon, and this distance right here is also epsilon, which means that this would be L plus epsilon, and this would be L minus epsilon. Will be the corresponding y values. So that's the restriction that we're going to put around this value of L. We're putting in essence a restriction on the range of this function. Basically what I want to do is I want to focus on the part of my function that stays between those two red lines. And the question that comes in, it talks about a corresponding value of delta. It says there exists a delta, and it also says that I'll be within delta units of C. So delta must be some sort of a restriction around C. And so what I can do then is I look at where these horizontal lines cross my function or hit my function, and I'm just going to drop a vertical line going down and do the same thing on the other line there. And those are the restrictions around C. You can see I now have a interval around C that I'm going to consider. Now generally what happens is these two distances to the left and the right of C here are different. They're not necessarily the same. So I'm going to call this one on the left delta sub 1, and that distance on the right delta sub 2. Depending on the function and depending on the point that you're working with, depends on whether or not delta 1 and delta 2 would be the same. Most of the time, like I said, we're going to find they would be different. So that means then this is the point down here, C minus delta 1, and this would be C plus delta 2. And the whole goal of this, it says for any epsilon greater than 0, any restriction we put around our limit, that there exists a delta. You can find this restriction around your domain, around C, that guarantees that as long as I stay within this restriction around C, that my function stays within the restriction around L. Okay? And if there's two values of delta that we're looking at here, and the definition only talks about one, we should at least clarify how we pick which one of the two deltas we'd go with. delta turns out to be the smaller of the two delta values. So I'm going to write it as the minimum, I'll just say min, of delta 1 and delta 2. So whichever turns out to be the smaller of delta 1 and delta 2, then you use that as your delta value. And that would guarantee that as long as I stay within that distance from C, that my function will stay within this epsilon units of L. Okay? It's definitely a definition that you need to understand, and definitely a definition that you probably need to review a couple of times. But I wanted you to see it and understand that that's the formal definition of what a limit is. All right. Let's take a look at another example here. We, for the most part, are not going to worry about some of these questions in here that ask about deltas and epsilons. I want you to see the definition and get an idea of how the delta, epsilon, L, and C are all related. But in terms of questions that I'm going to ask you about it, we're going to skip over those in this section. So look at part A only of example 2 here on page 35. I've got this graph here, and it's of a function f for which f of 2 is undefined. You can see that there's a removable discontinuity on this function at 2. And the question is, what number does the limit as x approaches 2 of f of x equal? All right, so let's write that out. The limit as x approaches 2 of f of x is equal to, again, what we're going to do is we're going to look at our function here at x equals 2. And we're going to consider what's happening on our function as I approach 2 from the left side as well as the right side, as we're approaching from both directions there. It looks like I'm approaching the same value, and that value here looks like it is at 4. So the limit is 4. We saw that happen, same type of thing happen with the first example, that when you have a removal of discontinuity, that the limit still exists. The function does not exist, but the limit does. Okay, in fact, if you wanted to make a note of that, f of 2 on this thing does not exist. Yet the limit does. All right. Let's take a look at example 4 there. We're going to skip over example 3. You can certainly look back at that if you want to and consider the limit on that one. But I want to look at example 4 and give you another method that we use to find these limits. We've seen graphical methods, and I'm going to show you a numerical method here. So we're just going to do 4b on this example. It says find the limit as x goes to 3 of f of x for the function f of x equals 0.2 times 2 to the x. Let me write down our function here. F of x is equal to 0.2 times 2 to the x. And the question here is to find the limit as x approaches 3 of f of x. Okay? So one thing that we can do if we want to do this in more of a numerical technique as opposed to a graphical technique, is we can take our calculator. I'm just going to switch over to my calculator here. And let's punch in the equation they gave us. So there's the function, 0.2 times 2 to the x. And I'm going to go up to my table here, and I'm going to just set it up to allow me to punch in just x values, any x values I want. So I'm going to put this into ask mode. Okay, for my independent variable. And then when we go to my table, you'll notice the table comes up empty because it's waiting for me to type in some x values, and it'll tell me the corresponding y values. So what I want to do is look at what's happening as I approach this value of x equals 3 from both the left side and the right side, and see what happens there. So if we, for example, were to put in 2.9, that's on the left side of 3, we'd be at a value of 1.4929. We can get even closer. We can go to 2.99, and we get a value of 1.5889. And we can go even closer. I'll go one more time here just so we can get a better idea of what value we're approaching. And it looks like we get 1.5989. And the goal here is I'm trying to get some values that are relatively close as I go through this process, and I'd say those two last values are relatively close, so I must be getting close to the actual limit. I got 1.58 followed by 1.59. It looks pretty close there in those two values. But that's from the left side. Let's consider what's happening from the right side. So let's start out at 3.1. That's a little bit further away from 3 on the right side. It's the same distance as 2.9 was away, but we'll start there, and we're at 1.71. And let's get a little bit closer, 3.01. 1.61, that's not too bad. Let's get even closer, 3.001. And I get 1.6011. So at 2.99, or excuse me, 2.999, I was at 1.598. And at 3.001, I was at 1.601. So I can see from the left side I'm getting closer and closer to 1.59 or 1.598 really. On the other side I can see that it's getting closer and closer to 1.601. So if I'm trying to make a guess here as to what value that I'm approaching, it looks like I'm approaching 1.6 from both sides. So my conclusion here would be that the limit is equal to 1.6, looks like. So that's how I can use my calculator to come up with a numerical solution to this. And obviously you can keep going with this if you need to use a couple more values to see that you're getting closer and closer to 1.6 from either side, but I think we can see that with that example there. Okay? All right. And that is the end of this section.